I see Dr. Nielsen-Gammon has joined us. So, good
Let
morning.
me make him
Morning, John.
co-host.
Yeah, so John, if you could hold off sharing your screen for just a minute, and I'll introduce you, then we'll get started. And I'd like to thank everybody for coming to the inaugural BEG Friday seminar series, and I'm co-hosting this with Priyanka Pariwal, and so we really appreciate y'all spending your morning with us. And it wouldn't be the inaugural meeting if we didn't have little delays and hiccups. So this is right on par with things. So and let's see, I guess we'll maybe hold our questions till the end, and I'll try and either read questions in the chat or we can unmute ourselves and have questions after about probably about 9:45 or so. So with that, I'll introduce our speaker, Dr. John Nielsen-Gammon. He's been a faculty at A&M since 1991. He's currently the Regents Professor of Atmospheric Science and also serves as the Texas State Climatologist and Director of the Southern Regional Climate Center. He graduated from MIT with a PhD in 1990. He does research on various types of extreme weather, from droughts to floods, as well as air pollution and computer modeling. As the Texas State Climatologist, he helps the state of Texas make the best possible use of weather and climate information through applied research, outreach, and service on state-level committees. He is a fellow of the American Meteorological Society. And just as a side note, if you work in the water world in Texas, you certainly know of Dr. Nielsen-Gammon's work, and so we're really very privileged to have you come and virtually and speak to us. So thank you. I think you can now maybe share and you're muted, I think, so you might need to unmute.
How about now?
Yes.
That's good. Okay. Yeah, sorry for the delay. I had the time wrong, and then Zoom wanted to update, and so I'll just try to make up for it by being especially insightful and concise in my comments, and we'll just see how it goes from there. So I'm going to talk about climate change and drought in Texas. I know I'm not in presenter mode, but I like being able to see the slides as they come along. And I'll be highlighting several pieces of work by my group and other groups that provide information on this. And it's, as you'll see, it's not the whole story yet, but we're making progress on it. So this article came out about 7 years ago now that was sort of a wake-up call for those of us in Texas about how drought in the future might be a really serious problem. What they did was they looked at soil moisture in two regions of the United States, the high plains and the Southwest, and they both compared paleoclimate information from tree rings on drought severity to what climate models were projecting. And you can see that the drought index and soil moisture levels as estimated from the models were dropping off a cliff starting really around 2000, so that we're already in a decline according to the climate models. Now, as with most studies, they didn't really focus on Texas. In fact, only a small fraction of the Great Plains region is Texas, and none of the Southwest region was Texas. So it wasn't immediately clear how much that applied here, although the fact that it's brown in Texas indicates that there's a decline going on there as well as elsewhere. And you notice that's projected over most of North America, despite the fact that much of North America is forecasted or projected to have increased rainfall. This other study I want to highlight focused on the Southwest, but they did some neat computer experiments to try to diagnose what was going on to producing the dryness in the models. And they're focusing on summertime soil moisture. That's when soil moisture is most important for agriculture and other purposes. Each one of the gray lines is a running mean of soil moisture from one of the models, and the brown in the middle is the average of all the models. And you can see it has this sort of dropping off a cliff behavior starting in the 1980s and 1990s. And what they did was they ran an experiment where they kept the precipitation from the future simulations, but constrained the temperature and humidity to be similar to the present day climate. And some models produced wetter conditions and some produced drier conditions. The average was slightly wetter. The background, by the way, is the soil moisture pattern from reconstructions from observations, which shows the big swings in the Southwest. The 1920s was a wet time. As we know, the Colorado River Compact out there was developed in the 1920s when there was plenty of water. And there was also plenty of water in the 80s and 90s, but it's been plummeting since then. So that's what precipitation does. Precipitation doesn't explain why that drop is happening. And because these are ensembles of models, they also won't capture the natural variability of the drought. They're just going to capture the overall trends. Over here on the right, they're keeping the precipitation the same as the present day, but they're allowing the future temperatures and humidities to influence things. And that does show the decline at about the right time. And you can see, if you put it all together, that decline is really driven by the temperature and humidity. So we have basically increased evaporation rather than decreased precipitation. And in the bar chart form, yeah, the evaporation effect is much higher than the precipitation effect, leading to drying conditions according to the model projections. Well, we didn't do that sort of fancy diagnosis, but we did get one of those authors to focus on Texas in their projections of future climate. So what we found out is, yeah, not surprisingly, we have these trends in temperature across the state of Texas. No place is immune from that. Basically, the dark red line is showing average temperatures across Texas, decadal scale, with the sharp increase really kicking in the 1970s and 1980s, which is over that period even faster than these various global averages from models and observations. At the same time, precipitation is highly variable across the state, as we know from 2011 and 2015. But the overall trend is upward, at least in the eastern 2/3 of the state, increases of 10% or more over the past century, whereas in West Texas, the century scale trend is essentially zero. Now, for soil moisture in Texas, we looked at West Texas and East Texas, and in the tree ring reconstructions, you can find some periods where conditions were persistently dry for long periods of time. And those are times when the average drought conditions were approaching -2 on the Palmer Drought Severity Index. Here's what you get in the model projections for West Texas and East Texas. They're both fairly similar. What you're seeing is the model average. So the natural variability is sort of hidden out of this, but it's normalized. So -1 is one standard deviation below the historical annual average. So that's sort of approaching drought conditions. -2 would be severe drought. And what we see is all of those measures of drought decline. Now, each one is different and each one sort of needs its own interpretation. The soil moisture at the top 30 centimeters declines the least. And in fact, about 25% of climate models say that the topsoil moisture will actually increase, that the precipitation increase will be large enough to overwhelm evaporation. The middle line is the Palmer Drought Severity Index. There's actually some question as to whether the way that index works actually properly factors in the effect of temperature. It may overestimate the effect of temperature, so I tend to disregard that one. The 2-meter soil moisture declines substantially, and that's in part because it has much less variability than the topsoil moisture. So a similar decline in moisture content shows up much larger when you normalize it. Now, these shifts in the drought indices and soil moisture are mostly reflecting a shift in the mean toward drier conditions. And of course, that means that very dry conditions become much more likely. And the drier you get, the farther out to the tail you get, the greater the relative increase in odds. Okay, so that's what is projected in the models, but models are only one tool for understanding what might happen going forward due to climate change. And you'd like to have all lines of evidence lining up. If you just have the models, there's not very high confidence unless you can fill in some of the gaps in the other two. So the three ways of identifying a trend and attribute it to climate change is, first off, do we actually see such a trend in the observations? Do we get consistent projections in the models? And third, is there a good reason for a trend? Is it logical to expect a trend given how we know that the climate system works? So I'll give you an example, a simple example first off, which is extreme cold conditions. So in this case, we have a clear historical trend, which is that extreme cold in Texas is becoming milder. We have consistent model projections, which say that extreme cold in Texas should be becoming milder. And we also have a physical understanding of why that ought to happen, which is essentially that our cold weather comes from the Arctic and temperatures are going up everywhere, but they're going up especially rapidly in the Arctic. Now, despite this, there have been studies coming out looking at extreme cold in Texas that said, or at least were interpreted as saying that climate change is making extreme cold more likely. But the papers didn't actually say that. What they actually said was that climate change influence on Arctic sea ice is making the weather patterns associated with extreme cold in Texas more likely. So and my dog is really excited about this concept. But so if you break it down and think about it logically, to get extreme cold in Texas, you need to have a weather pattern that allows for extreme cold, and then you need to have the extreme cold temperatures. In other words, what's the odds of getting that weather pattern? And given that weather pattern, what are the odds of extreme temperatures? Well, saying that the odds of that extreme weather pattern are increasing doesn't tell you anything about the odds of extreme cold given that weather pattern. And in fact, because temperatures are warming everywhere, we know that the odds of extreme cold given that weather pattern are decreasing. So those studies basically were looking at one factor of extreme cold, but they weren't looking at the overall picture. And the overall picture is consistently saying we're going to get less occasions of extreme cold going forward than we were in the past. Now I'll make another qualification of that, which is also going to come up in the discussion of drought and extreme rainfall, which is in reality, we went through this basically 30-year stretch between 1990 and 2020, where not only did we not get any of these, once every few decades extreme cold events, we also didn't get any once or twice a decade extreme cold events that had happened consistently prior to 1990. And so presumably we were in one sense lucky to have avoided cold weather that should have happened even given climate change. On the other hand, that meant that the grid in Texas had not been stress tested with serious cold prior to the super serious stress test of 2021. So it left us a bit more unprepared than we would have been had we seen similar weather in the past, in the recent past, when during the the ERCOT independent grid era. So why am I mentioning those past 30 years? Because climate change trends, when we talk about them, we're talking about how the odds are changing. So in other words, we're less likely to get extreme cold in the future compared to what the odds were in the past. Now, in reality, we sort of beat the odds by not having any extreme cold for 30 years. So if you're talking about what's actually going to happen to extreme cold, we're probably going to see more extreme cold in the next 30 years than we did in the past 30 years. Maybe not the super cold like 2021, but more fairly cold events, just because the odds say it's more likely we'll see something like that than the odd gap in extreme cold that we actually experienced over the previous 3 decades. So climate change trends are talking about what's likely to happen in the future compared to what was likely to happen in the past. Okay, so now let's get back to drought. And first off, the question on the top, is it more droughts or more aridity? Technically, a drought is a temporary phenomenon. But if you look at those graphs that had soil moisture decreasing, it was decreasing systematically. It wasn't like we were getting bigger swings in soil moisture from wet to dry, according to the models, but we were actually getting lower average soil moisture. Technically, that means aridification. It means that the climate in Austin, say, becomes more like the climate in San Angelo. And San Angelo doesn't have more droughts than Austin does, but its droughts are drier and its normal conditions are drier. And so there are impacts for everything that relies upon water because of that. But just saying that it makes droughts worse is on the one hand only talking about part of the problem, and on the other hand glossing over the fact that even when you're not in drought, things are going to be drier. So the factors that tend to drive drying are the changes in temperature. Because temperature is going up, it makes for greater evaporation. Another thing that drives drought intensity specifically is when you have bigger swings in rainfall from month to month and season to season. This is something that climate models tend to project. We don't detect such a trend in the local observations, but on the other hand, the extremes are large enough that you wouldn't expect to be able to detect a trend of the magnitude that the climate change models are projecting. So it's a small trend, but it's a factor that may be leading to more intense droughts. And also changes in rainfall seasonality, by which I mean climate models in general forecast either a bigger increase or a smaller decrease of rainfall in winter compared to summer, where it's a smaller increase or a bigger decrease. And since droughts have their biggest impacts in summer in Texas, a shift in the seasonality of rainfall from more rain in the summer to more rain in the winter would mean that we'd have more intense summertime droughts as a result of that, when this intensity really matters. Okay, now the factors that we know are going on that would sort of reduce drought. We've got basically changes in plants due to the increased carbon dioxide directly, which among other things improves water use efficiency by plants. They don't need to evaporate as much water to get the carbon dioxide they need from the air. And that means that plants do just as well with less water when they have more carbon dioxide all other things being equal. And if you have less water being drawn from the soil, then the soil moisture is improved. So that factor is working against those other factors. And then for various reasons, I've got 3 bullet items where the situation is unclear. And it's unclear for different reasons for each of these bullet items. On the one hand, changes in annual precipitation. That's unclear because climate models don't have a clear projection there. It's like the slight majority of climate models say that precipitation ought to decrease. As I mentioned, though, our historical trend is for precipitation increasing. And based on our knowledge of physics of the climate system, we don't have a good expectation for what should happen to annual precipitation in Texas. So very unclear how that will affect things, which is unfortunate because changes in precipitation can trump any other change in terms of making things drier or wetter. Next up, changes in the rainfall extremes and individual storms. There we have a clear trend, which I will talk about later. But the kicker with this one is that when you try to translate that into drought impacts, it really depends upon what type of drought you're talking about. Sometimes it helps, sometimes it hurts, and we'll get into that in a bit. Lastly, changes in biomass. That could potentially lead to greater water demand by plants if they actually end up growing more. On the other hand, it's not clear that an increase in overall biomass should at all be interpreted as having a causal effect on conditions becoming more arid. It sort of depends, again, on what type of drought you're talking about, because obviously the plants are doing all right. Okay, I have not seen a study that's actually looked at all 7 of these factors, but we get at least a handful of them from this paper that came out last year that started out by looking at seasonality in the title, but actually covers many of those fundamental factors that I mentioned driving drought. So first off, precipitation. And we're looking at the annual mean trend in percent per decade. In context, what we've seen in Texas on average is a plus 1% per decade. So if you're looking at historical trends on this map, it would show up as the light green that's dominating the eastern United States. The average model projection is smaller than that, and it's on the drying side. But this cross-hatching means that there's at least 25% of models, so a quarter of the models, on one side of 0 and at least a quarter on the other side of 0. So it's really not clear what's going to happen to rainfall in Texas. We're sort of stuck in between where things are definitely going to get drier, such as northern Mexico, and where things are definitely going to get wetter, such as the Midwest. So at least that means we probably won't see a big change in rainfall. All right, evaporation. I mentioned evaporation was the really big driver of why things get drier in the Southwest. So in that context, it seems a little weird to see mostly green out there or cross-hatching. Where's that strong drying signal evaporation? Well, it turns out that with higher temperatures, you don't actually get more evaporation. You get faster evaporation. And the reason you don't get more evaporation is because you can't evaporate more water than you get from rainfall or snow in the first place. There's a limit to how much you can evaporate. So you get drier because things dry out faster. But actually, the total amount of evaporation doesn't change much. Okay, soil moisture. And here, this is consistent with the graphs I showed earlier, that models are systematically saying that soil moisture will decrease across almost all the United States, even those places where they get more rainfall. And now we've actually got numbers here. So you get a sense of the magnitude. In Texas, the average projection is about a decrease of 1% per decade. So at least in a crude sense, the projected magnitude of soil moisture decrease is similar to the historic increase of water availability from the increase of precipitation we've experienced in the past. So according to this, the model projections say that the overall wetting trend we've experienced in Texas would reverse itself. If we look at deeper soil moisture, basically the same picture, not as clear, and also not as systematic. So this is the opposite impression as you got from those graphs, because the graphs are normalized, and this is absolute numbers. So the absolute change in deep soil moisture is smaller, and it's even smaller than the surface soil moisture. The reason for that, we believe, is that deep soil moisture decreases primarily from being drawn out by roots from plants and trees and so forth. And if the plants are more efficient at their water use, there's less demand for water from the deep soil, whereas you can get evaporation directly from the top of the soil, and so that's drawing down soil moisture at the top. Okay, the runoff projections are filled with cross-hatching, which is to say, again, at least a quarter of them all say less runoff, a quarter say more, but the average is systematically an increase in runoff. And so that's a mixed bag for drought. On the one hand, increased runoff implies increased water inflows into reservoirs, which is nice for surface water supplies. Now, it may be more erratic, which could be a problem. You may have to worry more about flooding, which could be a problem. And you also have to worry about evaporation once the water's in the reservoir. But at least the runoff part is not too bad there. It shows at least a good possibility of an increase. The plot on the right is what in the model is total runoff, which includes surface flow plus subsurface flow, which includes infiltration into aquifers. And that's a smaller number, which indicates, partly reflecting the fact that the soil moisture decrease is saying you're basically getting less water soaking in and more water running off, which means, runoff is great for surface water supplies, but it's bad for agriculture. It's also bad for aquifer recharge for groundwater supplies. So based on this, at least with the model projections, we get a different picture for surface water supplies than groundwater supplies, although they're both being affected by a complicated set of factors, including, of course, changes in water demand, which are affected by climate change in various ways also. Okay, I'm going to look finally a little bit more closely at the increase in precipitation extremes, which by itself would drive part of that increase, if not all of it, increase in runoff as opposed to infiltration. And this is a paper that we actually submitted last week, looking at extreme rainfall trends in the southern and southeastern United States. So the part of the motivation for this was the update in the official numbers for 100-year rainfall amounts and so forth. The blue is showing the old numbers. So for example, for Austin, it had been estimated that on average, once per century, you'll have a day with about 10 inches of rainfall. Now the color shows what the updates come up with, which is now in Austin, more like 12 or 13 inches of rainfall. And that's a big difference. It makes a big impact on on floodplains, margins and so forth. And we also see a big increase around Houston and down toward Corpus. And overall, we see more areas with increases than decreases. Now, I'll argue that the reason there's more areas with increases than decreases is because of climate change. However, it seems apparent from this plot that the reason the increase is particularly large in Austin and San Antonio and Torre del Rio is because the analysis is now resolving the Balcones escarpment, the fact that it really is flash flood alley and air hits the hill country, rises and produces greater amounts of rainfall. So this is partly the increases in local values in Austin are partly due to climate change and partly just due to a better baseline estimate in the first place. So we wanted to see what's going on overall. Now, climate models predict an increase overall. Here's two different models, and they're showing the increase in basically the annual maximum daily precipitation. But I want to point out two factors here. First, that's basically across the board increase. And secondly, there's a lot of detail that's probably not actually climate. These are two different models. They give you two different detail patterns, but the overall trend is the same. So don't focus on what's going on in a particular location if you want to see what climate's doing. Focus on what's going on over a large region, because you get very different pictures at different locations. Here's the annual maximum daily precipitation in Harris County using basically the longest term station available. And Hurricane Harvey is this dot that's way up here, 12 inches in 24 hours at this particular station. And the blue line is the estimate of of the 100-year rainfall amount taking climate change into account. And it shows a pretty big increase, but just go down a couple counties to the south, Brazoria County, almost no increase according to the historical statistics, even though they've actually seen 26 inches of rain in 24 hours. And now climate change is not going to affect two nearby counties so dramatically differently. That's just basically, that's just the randomness of the weather as to which places will get an extra large trend and which places might have seen no trend whatsoever. So here's the county values of the expected one-day precipitation amount that should happen once per century, just so you get a sense of the overall pattern. The risk is higher along coast rather than inland, presumably partly because of the effect of tropical storms and hurricanes. But looking at the county scale, there's a lot of noise here. So if we aggregate it into different regions, we get a much more coherent pattern that makes physical sense. Southeast Texas is the big loser here. They have the largest expected amount. You can also see the enhancement associated with the Balcones escarpment and a very systematic decrease inland, except for places where you actually start reaching higher terrain again. But the important result is on the trends in extreme rainfall. And even aggregated, you get the same sort of spatial variations that we saw in those model results that aren't necessarily trustworthy. But again, if you look at the big picture, there's a lot more green than orange. And so essentially this saying over the past 40 years, the expected value of the 100-year rainfall event has gone up by 10, 20%. Well, let's go ahead and aggregate this using a statistical model to see what we get for 100-year rainfall event and 2-year rainfall event over the entire region. And the green is using the full data set. The other colors I won't talk about. They're using truncated data sets. We're looking at the importance of having a lot of data. But in any case, these are 95% confidence intervals. So there's a clear upward trend historically, and the trend is larger for the more extreme rainfall amounts, talking about 11% increase over past 4 decades in the expected amount. You see the same basic pattern for the Gulf Coast region. The Southeast turns out to be sort of, because it's a smaller portion of the study area, there's more variability, and so the confidence intervals include 0. So it's not possible to pin down the trend very well over just a small multi-state area. But if you look at the whole Gulf Coast, or even the Gulf Coast plus Southeast, you do get decent estimates of the trend. This is saying that extreme rainfall is increasing. This is also saying then that the fraction of runoff ought to increase compared to the fraction infiltrating. So summarize some of the key factors here. Probably soils are getting drier. We understand why that should happen. We see it in climate models. We don't have long-term soil moisture observations, so we can't quite have all 3 of those factors lining up. That's why I only say probably. Expected runoff increasing? Yeah, maybe. Certainly, we see expected intense rainfall increasing, as you see in the bottom bullet. But because soil moisture is decreasing, so that's sort of a bit of a trade-off, at least for large river basins. We may actually only see the upper end of floods become worse. In urban areas, decline in soil moisture doesn't matter. Much of the land surface is impervious, and so extreme rainfall increases runoff, period. And also lake evaporation increasing is a clear trend, although I haven't quantified that. But temperatures are going up, so you can't help but have higher lake evaporation too. All right, thank you for your patience. Sorry for being late and getting this going. I'll be happy to answer questions.
Great. Thank you, Dr. Nielsen-Gammon. Let me look and see if there's something in the chat here. So you can either unmute yourselves, or if you'd like to put something in the chat, I'll read it off here. So looks like Michael Young, Dr. Young says here, sorry, this is moving. Another question. The National Weather Service mentioned that predictive skill and precipitation forecasts around San Antonio are the lowest in the country. With the drying trends, would the variability change?
Well, let's see. So that's an interesting question, because we talk about rainfall becoming more erratic, but that doesn't mean the same thing as rainfall, say, becoming more chaotic and less predictable. My expectation is that the predictability of rainfall in San Antonio will not change much, except for the fact that as the jet stream moves farther north, we tend to have greater fraction of our rainfall from tropical type weather and less from what we call extratropical or mid-latitude weather disturbances. And tropical weather is inherently a bit less predictable. So I would expect predictability to decrease slightly. The good news is it shouldn't increase as much as our ability to forecast weather better is going to improve going forward, because it's been improving in the past. So we'll be able to forecast rainfall better, just not as well as we might have been able to.
And I actually skipped his first question. It says, though, Dr. Young says, though the model shows higher water use efficiency of plants in arid and semi-arid settings in future Austin area, question mark, total root water uptake should be the same, keeping soil water stocks equal in time. Does the model calculate water use efficiency, or is it a tuning variable in the models?
Most of the biosphere models in GCMs are basically taking the direct effect of carbon dioxide and transpiration and factoring that in for evaporation rates. They would do a much worse and cruder job in estimating how much total biomass changes given plant community, and even poorer job predicting how plant communities would change as the changing climate favors some plants over others. So it's a bit of a mixed bag on that part. The direct effect should be fairly well estimated, but some of the indirect effects not so well.
Great. Geeta Prasad asks, she says, thank you for the edifying talk. Given that drought projections in Texas rely on multiple variables that have high uncertainty in climate models, how can we talk about that uncertainty with stakeholders in a maximally decision relevant way? In your experience, is it effective to talk about the percent of models that agree on a given signal?
Well, I just gave a talk on that subject. And I did talk about percent of models that agree. But I think it's important to talk about, which, there are different ways of conveying the levels of uncertainty. I think it's important to clearly distinguish those in whatever way works. I use percent of models because that was available in the graphics clearly enough. But I think stakeholders need to know that soil moisture in and of itself is almost certainly going to decrease, whereas runoff, it's unclear what's going to happen. It probably would increase, but not necessarily. And so you can hang your hat on some aspects of climate change, and the rest of it still can't say specifically. And the other important lesson, I think, that I want to make sure that people get out of this is that you have to be clear about what type of drought you're talking about. Because the drought that a plant experiences is going to be different from the drought that a reservoir experiences, but it's going to be different from the drought that an aquifer experiences.
Okay, we have a question here from Matt Nelson. Says, could you explain a little bit more the mechanism behind that lower soil profile drying much more as a trend than the topsoil? Is it a matter of occasional quicker total soil water loss occurring in topsoil when it does occur, thereby creating an occasional ratcheting down each time of the lower soil layer?
Well, the increase in deep soil is larger than topsoil when you normalize by variability, but in absolute terms, the decrease in topsoil moisture is larger than decrease in deep soil moisture. So basically, what's that saying is, you don't have as much variability in deep soil moisture, and so you very quickly, your typical conditions become similar to what you would have regarded as drought in the past. But the absolute loss of water is not as great because the topsoil is more sensitive to what's going on in the atmosphere, and it's less sensitive to how plants are responding. Sorry if I didn't explain that clearly enough, but there's still time for questions.
And let's see, Michael Young says again, plants will eventually adapt to lower total precipitation by pushing roots deeper into the soil and often creating shallow root systems to capture lower precipitation events. I guess that's more of a statement than a question, perhaps. I don't know, Michael, you want to clarify that?
It's more of a statement. I mean, as the regional climate gets drier, the plants will adapt by pushing more carbon deeper into the soil to get deep soil water stocks, right? So that would explain drier, deeper soil. And the shallower soil is going to be, as John mentioned, is going to be adapting to a larger number of smaller events, precip events, right? So they're going to capture those small events that maybe water penetrates down 30 centimeters or so. But overall, the soils are going to, they should dry even with higher CO2 amounts, I would expect.
Yeah, I'm not an expert on plant response, but it's not clear to me that roots will generally become deeper because of the water use efficiency effect.
Yeah, I mean, if you just have more biomass per kilogram of water uptake.
Right.
Okay, we've got a question from Javon Harding at the Water Development Board. So a common way to implement recharge in groundwater models is as a percentage of precipitation. But based on your talk, it sounds like we should be decreasing future recharge, even if we expect precipitation to stay relatively constant to account for the other drying factors. Is that correct?
Absolutely correct. Yes, that's an important point. The fractional recharge should be decreasing.
And that sort of touches on a question that I had for you, from the water planning perspective, and you touched on your AGU paper that came out a couple of years ago. But it was really apparent to me that in your talk, how as a state, we're planning for these droughts. We're looking in the rearview mirror, as you say, at these droughts, and we plan for the drought of record. But really, it sounds like we should be planning for both, and it sort of touches on what Javon is saying there, that we should be planning for this overall aridification as well as maybe droughts, but there's going to be droughts worse than the drought of record. And so do you have any thoughts just on general, what should planning look like, or future model scenarios? Should we be, putting together some sort of synthetic hydrograph that will help in our forecasts for, groundwater models in particular?
Yeah, it's challenging. I mean, the thing that seems to be clear, even given all the uncertainties, is that future droughts are going to be different. They're going to happen in a warmer environment, and so the consequences will be somewhat different, and that's challenging for water planning because of the uncertainties. You don't know how different you're going to be. You don't know what the appropriate target is. I think it'd be useful at least to have some sort of have one or a small number of potential future scenarios where you say, okay, recharge decreases by 10% or whatever it is, that individual water suppliers and water planners can sort of run those numbers on. And it sort of has to be done in the context of the historical drought record, because everything's calibrated to that, but you can do that and get a sense of at least what, how big the numbers are we're talking about, how different things might be. And that would be useful information.
Mm-hmm. Great, thank you. Well, we're approaching 10 o'clock, and unless there's no further questions, I'd like to really thank you for your talk today. I certainly was disabused of some certain preconceived notions I had, and so I really appreciate your talk and the references that you provided as well. This was our inaugural talk, and so every Friday morning we'll have a talk. We have a future. So for next Friday, on the 16th, we have Richard Krupp, who's going to be speaking about developing groundwater maps for arid regions in Africa. So sort of following up on sort of climate and aridity issues and topics. So with that, I guess we just want to say thank you again, and appreciate your time. Thank you for everybody for coming.